Let me get started. And thank you for the inviting me. And if I look a bit out of it, it's because there's a huge temperature difference between here and Montreal. I had to check because Canadians work in Celsius, so it's 50 Fahrenheit in Montreal right now. And we had snowstorm 2 weeks ago, so it's a huge change. And I had to walk here for 30 minutes, so that's why I'm a bit out of it. But just need to acclimatize, and I think I'm okay. All right. So again, I thank you for the invitation. I'm really glad that I could fit this in during my relatively short visit here. I'm only here for 2 days. So I'm a theoretical astrophysicist and assistant professor at McGill. And I lead a group studying the formation of planets and stars with the focus on exoplanets. So I think this crowd knows well that in astronomy, much of the research is driven by discoveries and observations. So even though I'm a theorist and my group is a theorist, much of our research questions are indeed motivated by some of the puzzles that have emerged in the detections and observations of planets outside of our solar system. So I'd like to begin with, if I can progress. I'd like to begin with the short overview of the history of this field. So this is cumulative number of detections of exoplanets as a function of discovery year. This is all public. You can just go to NASA Exoplanet Archive and download the data or just look at the plot. They pre-make this plots and update almost weekly or even daily. So if I were to begin with the very first detection of an exoplanet, for some reason it's not on this plot. It actually was made in 1988, and I have to mention this because I'm Canadian and that was made by Canadians. Although it was extremely controversial at the time. It wasn't until the early 2000s where people went back and verified that indeed this really was a bona fide exoplanet. So if you have not heard about it, that's probably the reason why. And then the researchers, being Canadians, they were very careful, like not to oversell anything, almost to their detriment. But the reason why it was so controversial, it's because detecting an exoplanet is extremely difficult. I mean, I think I'm talking to a crowd with like expertise in observations and taking like astrophotographies and all that. So we're trying to detect something that's like 100 times smaller than the star that it orbits around and like million times lighter than the star that it orbits around. That's a really tiny signal, and it's really hard to get it out of all the noise that comes from your instrument and also from the star. So maybe like during the solar eclipse, I think it was partial eclipse on this part of the continent. Yeah, so we were very fortunate to have total eclipse. But like even with a partial eclipse, if you look through the solar telescope, like you can actually see a lot of like prominences and activities that happens on the surface of the sun, especially right now because we're at the sort of the tip of the activity cycle. Like all those activities are actually really bad for planet detection because like that will come up as a spurious signals. So like you have to beat all those noise, and that's extremely difficult. So the discovery that many people know about is the one that was made in 1995 and won the Nobel Prize in Physics in 2019. This was the first detection of an exoplanet around a sun-like star, and that is an important qualifier around the sun-like star because it's not like astronomers weren't doing anything in the intervening years. They were finding planets. They were just around very weird objects like compact objects or something that's like not even a star. So the reason why around a sun-like star is important is because now we're getting to the question of, are we living on a special planet and special planetary systems in our galaxy and in the larger cosmic context? But if I were to pick out a single mission that really revolutionized this field is the Kepler Space Telescope that was launched in 2009. And the reason why this was so revolutionary is because he found like thousands and thousands of exoplanets. And it's not even just a sheer number. is the fact that the majority of those thousands of planets looked nothing like what we see in our solar system, and furthermore, it was like nothing that we expected. Like we expected those planets should just like not exist at all. So the fact that they are so abundant in our galaxy came as a huge surprise. So just a personal anecdote here. I was an undergraduate student at the University of Toronto at that time, and I knew that I was interested in like astronomy research, but I wasn't sure which kind of astronomy that I wanted to get into. So I went to a lot of like seminars, colloquia, even like public talks like this, like to figure out what really excites me. So around this time, Toronto had a lot of visiting speakers telling us about like what Kepler is finding, like all that data that has like no explanation and completely overturning all our prior thoughts on how planets should form. So I thought that like even as someone like so young at the time, to enter a new field, like maybe this is a field where I could make a meaningful contribution given that there's just like so much mysteries. So I entered graduate school in 2012 at UC Berkeley, and I've ever since then I've been in this field, and it's been like such an excitement. So you will see this huge rise in the number of detections. That's because the Kepler, they decided to finally make their data public. So all this is public data. So now we have more than 5,000 detected exoplanets, which is great because that is a big enough sample to figure out are there any patterns, are there any trends at a like population and demographic level, so that we can get at the question of how do we place our solar system in the larger context. So I mentioned a few times about how all the planets that Kepler found look nothing like what we see in our solar system. So let me describe that a bit more. So this is solar system. The sizes are to the scale, distances are clearly not. But the point is our solar system is quite ordered in that on the inside, close to the sun, we have this small rocky planets, Mercury to Mars. Beyond that, we have this huge giants, gas giants, Jupiter and Saturn. And beyond that, we have Uranus and Neptune that we call as ice giants just because they're so far away. But you can think of this as object with a relatively thick gas layer on top of a rocky body. So those first discoveries of exoplanets, like that was made in the late 80s and early to mid 90s, the reason why we could detect them at all is because they were really weird. So they're what we call the hot Jupiters. So you literally just take a Jupiter-sized object and put it super close to its own star. I think most hot Jupiters are about like 4 times closer to its own star as compared to Mercury's sun distance. So they're really being scorched. And to this day, theorists still are debating how exactly we can explain their existence. In fact, there's a dedicated meeting going on 2 weeks from now to talk about this. So what did Kepler find? So Kepler found a lot of smaller planets, but again, these are very much close to its own star. In fact, many of them, even if you have like multiple planets, they're in very tight configuration. For many of them, you can fit like 5 planets or so, or 4 planets actually, 4 planets or so all within the orbit of Mercury. And that's quite common. Furthermore, most of those planets fit within the size range of Earth and Neptune, and that is surprising because in our solar system, we have a gap. There's no planet of size between Earth and Neptune. And just to give you some idea, Neptune is about 4 times as large as Earth. So we call them things like super Earths and mini Neptunes because from 1 to 1.7 Earth radii, those are considered as blown up rocky planets. So it's just rocky planets that's slightly larger than Earth. And from 1.7 to 4 Earth radii, those we call as mini Neptunes because they're like scaled down version of Neptunes with some rocky body with some gas layer on top. Okay, so if we get a bit more quantitative, there are 3 fundamental measurable parameters for these planets. That's mass, orbital period, so how close they are to its own star, and their size. So if you look at mass versus orbital period, again, this is all public data. You can go to NASA Exoplanet Archive to get all this data and check it for yourself. I've also plotted here the solar system planets in diamonds, just to give you that comparison. And first thing you note is there's not much overlap between the exoplanets and the solar system. Reason being that our solar system just happens to have small planets far away from our sun. And those are very difficult to detect outside of our solar system. So it's not that these don't exist. It's not that there are no solar system version 2. It's just that it's really hard for us to find solar system version 2. We don't have technical capabilities right now, but we might about 2 to 3 years from now. These exoplanetary systems, I plotted in different colors. Those colors correspond to different detection methods. I feel like this crowd already knows a lot about detection of exoplanets, but I will still go through them. So the blue one, I think this one everybody knows. Blue is transit. So this is what Kepler used. This is also what NASA's TESS is using right now up in the sky. It's finding planets as we speak. So this one's simple. You just stare at a star and just collect all the light that's coming from the star. But if the star has a planet orbiting around, then the planet can block out certain parts of the star, right? As long as the geometry is right, so that it's actually blocking across our line of sight. The frequency, as in like how often that dimming in the light that you measure will occur because the planet is blocking, that tells us the orbital period. And how much of the dimming occurs, that tells us the relative size of the planet with respect to the star, like how much of the star it's blocking. So transit tells us size and orbital period. Now the black points, those are radial velocity, and this uses the Doppler effect. So same thing as in when you're like waiting for the lights and trying to cross a street, and a car just like zips by, and if it's coming towards you, there's an increase in frequency, so you hear the higher pitch, but as it goes away from you, you hear lowering pitch because the frequency gets lower. Same thing happens here, except with light, because light is both particle and wave. So in this case, what we're measuring here is we're measuring the gravitational effect of a planet tugging on the star, because planet has a mass. So as a planet tugs on the star, it causes a wobble of the star. The technical term is that there's a shift in the center of mass, and the star will orbit around the center of mass. So let's say I'm an observer here. As the star comes towards me, the frequency increases. As the star goes away from me, the frequency decreases. So that's going to cause a shift in when I collect again all the lights coming from the star, but not break it up into different frequencies. And there will be features in that measurements due to the chemical composition at the atmospheres of the star. So those features will undergo blue shift and red shift, and the degree of the shift tells us how far away the planet is and how massive the planet is. This red points over here, all the way over there, those are directly imaged planets. This one's simple to explain because it's literally just taking a picture of the planets while blocking out the light from the star. So this is an actual system. It's called HR 8799. It's a system of 4 super Jupiters very far away from the star, and all this light, that's a planet, and that light is coming directly from the planet. It's the planet is shining.
Can I ask questions, Sarah?
Yeah.
So those planets aren't emitting? Would it be better to do the direct imaging with an infrared telescope?
Yes.
It's a thermal emission.
Yeah.
If you see that in 20 years.
So clarification, is that,
Yeah.
is that reflected light off those planets from the star, or is it?
No, it's
Infrared-
it's
infrared
infrared emission from the planet. Yeah.
Which wouldn't that also be a form of like reflected starlight? But like delayed on or
No. It's literally just the planet being hot. It's a hot planet.
but isn't it hot because it's close to the star?
No. It's because the planet has formed, right? And there's a heat
Okay.
from the formation. Yeah.
Okay.
So that's a good question because this means this only works. Well, yeah, it's easier to detect planets that are very massive and very young, so that it's still bright.
A bit of radioactive decay, perhaps, too. Eh?
Not so much. Not so much, yeah, for these planets.
Question. You plotted the transit things on here on a mass on the vertical axis, and you mentioned that you have size. Is that presumed density? How did you get mass for the transit planet?
That's a great question. So the discovery is by transit, but I'm only plotting the ones that were followed up with radial velocity so that we can get the mass.
Okay.
Yeah. If you do go to NASA Exoplanet Archive, you have to be careful because they will just give you masses and you have to go to a separate column and to figure out how exactly they're calculating mass. Because sometimes they also give you expected mass based on some assumed mass radius relation. And you shouldn't really trust it.
Hey, Dr. Lee, on the very left-hand side over there, the period in days, that's the period of time it takes to revolve around its star?
Mhm.
And that's like, what, a 10th of a day or a 100th of a day?
1 day, yeah.
Yeah, 1 day. Yeah, there's 1 day.
That's 1 day. So the ones over here are like,
Less than a day.
wow.
Yeah. Yeah. Yeah.
Must be a very small star.
Yeah.
Yeah.
Yeah, those have special names, and we give like lots of different names, like lava planet, and like things like because it's expected to be molten, like completely molten, like it's a rock that's molten. And also we give names like ultra short period planets. Yeah. Right. So directly image. Oh yeah, I wanted to mention. So there's a future mission that's being planned. That the hope is to look at reflected light from the star, so that we can take a glint of like an ocean world, like reflected from the ocean if there's an ocean on the surface. But that won't happen until like decades from now. Right, so finally, the orange planets over here, those are microlensing planets. So this uses gravitational lensing effect. So let's say there's some like background source of light. And then let's say like background source of light over here, and then there's some foreground star, and you are all observers. Then the light gets deflected by the gravity of this foreground star. But let's say the star also has a planet. Planet also has a mass, so it's also going to act as a secondary lens. So all that deflection will show up as a magnification. So it'll show up as a sudden brightening of the light. So that also tells us the mass of the planet and also its orbital distance, orbital period. You might be wondering why it's like vertical, like why it picks out certain like very specific orbital period. That's because the lensing effect requires a very specific alignment, and that this has the highest sensitivity when the alignment sort of like agrees with the star planet distance. So that's why it picks out a very specific orbital period. So these are 4 major detection methods, and I will briefly mention this again when I talk about some of the future missions and how that will advance this field. Okay, so I've mentioned mass and period, but the third fundamental measurable quantity is the size. And in fact, we have most of the planets, we have the size and not so much the mass. Just to give you some number, I did tell you that we have more than 5,000 detected planets. So for all of those, almost all of those, we have the size. But in terms of mass, we only have mass measurements for like up to like 200. Because mass measurements is very difficult. So if you want to get a sense of that population level trends, we kind of have to go for the size. So this is size, sort of histogram, distribution, and this has been corrected for all that biases and observational errors that we've been talking about a bit. So just focus on the red point for now, because that is the more updated version. So we're going left to right, small to large, so rocky planet to more like gassy planet. And we notice right away that it's not flat, which means that there are certain types of planets that are more preferred by our galaxy. So in fact, we see that it's the smaller planets that are more preferred. We have a hint that it's the small rocky planets that seems to dominate the population. And just to be clear, it's not like these don't exist. It's just that we do not have the capability to detect them because they're so small. We don't really know how this will go. But we do know what's going to happen to the right. So we see that toward the larger and larger rocky bodies, there's a decline in the population. But then there's a sudden peak corresponding to mini Neptunes. So again, these are like some gas layer on top of a rocky body, but that peak is quite narrow. Like once you go beyond like 3 to 4th radii, which is about the size of Neptune, we see a sudden drop. And that tells us that in our galaxy, things like this gas giants are extremely rare. Very rare compared to the smaller planets. So that raises the question, like, why is it that our galaxy prefers the small planets over the gas giants? So now we're getting to the question of how planets form, and planet formation really begins from the formation of stars. And stars form what we call as a giant molecular cloud. As the name suggests, these are a cloud of mostly hydrogen molecules and some amount of helium and really tiny amount of metals. And just to be clear, when you hear astronomers say metals, we're just talking about elements heavier than helium. All of those are metals. So if you look at this, this is an actual scientific image from JWST. Just looking at one part of star-forming cloud, Orion Nebula. And you'll see that there are a lot of filaments, a lot of wispy structures, and that's because it's a really turbulent region. It's so turbulent, the Mach number goes up to about 9 to 10. And if I were to translate to miles per hour, I believe that's like 7,000 miles per hour. So you really do not want to be there. It's a horrible place to be in for us, but it's a great place for the formation of stars. Because there's going to be a lot of shock fronts that causes like a lot of clumping. And the clumps can get dense enough that it'll just collapse under its own gravity. But while it's collapsing, it's also spinning. And if any of you do any clay work and try to like collapse, like squish something that is spinning, you always end up with a pancake. So same thing here. We end up with the disk of gas and dust surrounding the young stars. So it is inside this disk in which the planets form. So we call them protoplanetary disks. So if I were to zoom in and cut a slice through this disk to look more closely at what exactly happens and how exactly the planets form. So a planet, if I were to describe it in its simplest term, it's literally, and I think I've been like keep saying this, but it's really just rock with some gas on top, right? That's what our Earth is really. And that rock and gas has to come from somewhere, and it comes from like all the dust and gas in this disk. But I keep saying dust and not rocks, and those dust grains are really tiny. And those like tiny dust grains somehow have to grow into this planetary-sized bodies like our Earth, which is like a few thousand kilometers. For now, we're just going to assume that that happened because we see planets. So we have the rock, and the rock is massive enough that it can gravitationally attract and form these planetary atmospheres. But as that is happening, the disk itself is also evolving, and that is important to keep in mind. The disk is losing gas, not all of it goes into the planet. So on the outskirts, the gas actually gets blown away by the wind heated by the star. The wind, what is powering that wind is the photons from the star. On the inside, the gas actually gets funneled onto the star due to the gravity of the star and also some internal processes within the disk gas. And we know this because we can actually directly observe the gas funneling onto the star by various ways. So overall, over like a few million year timescales, all the disk gas disappears away, which means that there's a very tight time limit for the formation of planets, especially if you want to create some like gas enveloped or planets. Okay, so again, going back to the question of why is it that we sometimes have the small planets and the large planets, and what favors the small planets. Let's now take a deeper look at how exactly planets become large and have that thick gaseous layer. Again, we're going to start with a picture that we already have a massive enough rock so that we can define some gravitational sphere of influence inside which the gas can be gravitationally bound to this rock. Now, that binding process, it's like the gas is falling onto the rock, and the falling is always some release of potential energy, and the release of energy is heating up the gas. So you actually have a temperature difference between the closer to the rock and farther away from the rock. And I think this crowd appreciates that the nature really does not like having temperature difference, right? It always likes to get rid of it and like to cool off. So that's what's going to happen. And if you have a gas layer that's cooling off, it's going to shrink. There's a very simple-ish demo that you can do like on Earth to convince yourself that a gas that cools is going to shrink. If you have an easy access to liquid nitrogen. So I unfortunately do not have easy access to liquid nitrogen, and I think I need like
in my other pants.
safety first to do that. But I found video on YouTube, so I think I will show that instead. But again, if you just have access to liquid nitrogen, it's really simple. You just need a balloon.
It'll work in your freezer too, probably.
Oh, and the audio is not showing up, but I think that's okay. The demonstrator is talking about the helium balloon, but that's a bit of a red herring for our exercise, so I'm gonna skip. That's just regular balloon with air, and that's a beaker with liquid nitrogen. And the demonstrator is going to put that in to quickly cool off the gas in the balloon. You can already see the shrinking, and it really. Oops. Okay, I don't know what's going on there. All right. Yeah, it is going to really. Yeah. Yeah, and that's because at the ambient temperature, there's now a temperature difference where it's cooler inside and hotter on the outside, so it likes to go back out. Yeah. Basically, the gas is being heated up instead. But yeah, so you can convince yourself that indeed, if a gas layer is cooling off, it's going to shrink. So what's going to happen here? If the original gas layer shrinks, then I'm going to have all this empty space to refill within the planet's gravitational sphere of influence. So I'm going to fill in with even more gas, and that is how planets build its gaseous layer. So that's a relatively simple physics. It's basically thermodynamics. And using that, we can write down just pen and paper calculation to figure out what are the key parameters that control whether you have a thick gaseous layer or barely anything at all. So there are three parameters. The first is time. And this one's simple. The more time you have to build your envelope, the thicker it's going to be. All it means is it tells you something about when you should create or assemble your rocky body. If the rocky body assembles early, then you have more time to build your gaseous layer. The second parameter, Z or Z, this is just the abundance of the metallic species. It tells us about like how much of the metallic species are there in this atmosphere, and metallic species really act as a polluter. And if you have a lot of polluter, it's harder for the envelope to cool, like because it acts as a blanket, right? It's kind of the same thing that happens in Earth atmosphere. So the less polluter you have, easier to cool, therefore easier to shrink, easier to accrete even more gas. And finally, we have how massive this rocky body is, and notice how strong this dependence is. By far, it is the mass of the core, the rocky body that controls most what kind of envelope that you're going to end up with. And that's because of the stronger gravity. So altogether, this means that the final fate of the planets, as in what kind of size of the planet that we're going to end up with, is kind of determined all at birth, like how massive that rocky body is and when exactly that rocky body assembles. So if we take sort of like a bird's eye view of, in general, what do we expect of the thickness of the gaseous layer for the different mass of the rocky body, and the color coding here corresponds to that accretion time. So purple are the rocky cores that have assembled so late that it barely had any time to build its gaseous layer. The yellow points are the rocky bodies that have assembled very early. So it had the full disk lifetime to build its gaseous layer.
Hey, Dr. Lee?
Yeah.
Quick question. If I jumped ahead here and you have it later, that's okay. So in our solar system, and I know you said there's not a lot of Jupiters, but in our solar system, the Earth, Venus, Mars, and Mercury collected a lot of terrestrial material, rocky stuff. Jupiter, not so much. Why?
So actually, this was debated, but I think the debate has been a bit more settled now. So if you probe the interior of the Jupiter, you actually have a lot more rocky material on the inside.
Okay.
Yeah, it's all sort of like concentrated.
Gotcha.
Yeah. Yeah.
Really weird side question on that. There's theories for very weird solid hydrogen stuff at the core of Jupiter, correct? Does that play well with terrestrial material, or
Solid hydrogen.
it's like for condensed, I think either hydrogen or deuterium. I don't know if this is your regime. It could be do you know much, or
yeah, so the face of the material is actually a bit weird, like not even just on Jupiter, but also on a lot of like exoplanets. It's just that we can't actually probe what's going on with the exoplanets. So if you do like sort of like first order like physics and like material like science kind of calculation, you end up with some like crazy stuff, like where I keep saying core and like rock, but if you actually place it in like the sort of like regime, like temperature and pressure where it is relevant for formation, it is so high that it's like a weird supercritical mixture between hydrogen and rocky material that might be like a plasma soup instead of a rock.
wow.
Yeah, so actually it's a very much an open topic, because that kind of regime is not something that we can directly test in a lab setting, because you're just gonna melt all your instruments.
Question.
Yeah.
Looking at this chart, would it be safe to say then that the gas giants in our solar system formed earlier? Even if just by a little bit, because then they had that condition where they had more time to accrete material.
Yeah. Yeah,
And
in
that,
fact, it's,
and the rocky interior planets were latecomers.
yeah, yeah. In fact, for Jupiter's, it's like a necessary requirement. Yeah. Right. Yeah. So if I do sort of like one-to-one comparison, like these are sort of like rocky planet, those correspond to mini Neptunes, and as I think the audience appreciates, like these are the giants, right? And notice how just like small of a parameter space the giants occupy. It just means it's really hard to. There's like a very stringent formation requirement. So the rocky material that you start with has to be very massive, and it also has to form very early. So you need to meet those two requirements, and that's rather difficult. Before I say more on that, this is all theory, but any good theories must be testable by actual data and observations. So if I compare this to actual data, that's how it looks. Like these are just select data where the mass measurement is good enough so that you can actually calculate the mass ratio between the gas layer and the interior rocky structure. So it looks like a relatively good agreement, except for some few points over here. These points are not that hard to rematch because this chart was made for a very specific metallic abundance and orbital distance. But the red points are a bit hard, but that's okay because red points are known outliers. Like these are known to be very, very puffy planets. They're so puffy that their density is less than cotton candy. They're called super puffs, and they require very special formation channels, and there are ways to explain them. That I'm happy to discuss if you're interested. But in general, sort of the flip side of the stringent formation requirement for the Jupiter is that the fact that our galaxy has so many of the smaller planets means that sort of the smaller core masses are preferred, and also this like late assembly timescale is also preferred, right? So why is that the case? All right, so let's now talk about the assembly of the rocky core that previously we just said we're just going to assume that it happens. So this is still a very much debated topic because we have to go from dust grain, which is about a micron. So I think that's like 10 times smaller than the width of the human hair. So that's really tiny. And you have to grow it to, again, like Earth-sized objects and even larger. That's like 12 orders of magnitude of a jump. That's a lot. All we can agree on right now in the community is that there must be like multitude of different physical processes that occur. Exactly how that comes about is still debated, but I can tell you in general what kind of physics must be involved. So the first step to go from like a micron to, let's say, like centimeter or so, that uses electrostatic forces. It's the exact same force that creates dust bunnies in your houses if you have not cleaned certain corners of your houses for a while. The exact same thing. And then from there to slightly larger bodies, let's say like a meter to larger, then you start to require aerodynamic drag. So exact same thing that you might feel if you go hiking. I feel like in this area it's not really true because this is very foresty, I find. But if you happen to hike in a very like open area, I don't know, go to the West Coast or like go to like Iceland or somewhere, and there's a lot of wind, then like it's really hard for you to keep on hiking. Like you have to work against that resistance from the wind, right? So it's the same physics of aerodynamic drag, although we're in a different regime because we're dealing with very tiny object that is working against the thick disk gas. But it's the same aerodynamic drag. And then from there, you can grow up to like kilometers-ish. Notice the very wide range here. That's because depending on who you talk to, like unfortunately, there's a lot of uncertainties that's like orders of magnitude large. But from there, let's say from like 1,000 500 to 1,000 to like something that's like a Mars-sized object, then you still require aerodynamic drag, but on top of that, now the rock is massive enough that its own gravity starts to matter. And then from Mars size to even larger object, now we're getting to the planetary size regime. All the aforementioned physics matters, and on top of that, we can now start to have the collision of mergers. So as in like two Mars-sized objects hitting each other and collide and just merge to even larger object. If you are more attuned to like planetary scientists, like they often call this giant impact. It's the same thing.
Quick question.
Yeah.
The dust grain all the way on the left, is that about that size, about akin to smoke particles?
Ooh. I think smoke particles might be larger.
Hmm.
Yeah.
Cool.
Okay.
Dr. Lee, so,
yeah.
and those dust grains, if they are metals, anything above helium,
Uh-huh.
they have to have come from a supernova?
Yes.
Well.
Okay. So if we're interested in the assembly of the planetary sized object, then we kind of have to focus on this final step of the giant impact or collision of mergers. And if you look at how can we bring two bodies together, that's actually going to be very difficult in the early stages of disk evolution when the disk is really full of gas. Because, again, these rocks have to work against all that friction that it feels against all that gas, and it's really hard for those rocks to deviate from its original trajectory. So you're going to have like all these rocks like nicely swimming in its original configuration without coming into contact. You have to wait until the gas goes away so that the rocks can perturb each other gravitationally and have them come into contact because of more of an elliptical orbit or more of an eccentric orbit. So, once you go through a series of those mergers, then you can have the final planetary system. We can also put a number to this. You have to wait until the last few percent of the disk lifetime for this to happen. Anytime before that, there's just too much gas. So that means there's a natural expectation from physics and astrophysical considerations. Why is it that sort of late assembly of this cores are preferred? Okay, so again, like this is theory, and all good theories must be testable by observations and data. How can we, is there a way to directly test this? Couple ways to test this. The first is, again, to go back to those fundamental measurable quantities. Now, if we combine the size and mass, then we can get the density. So we can get some sense of like what are the planets made out of, at least at a basic level. And again, so far within the limited sample that we have for the mass measurements, here the contour lines are the theory, and the dots and triangles are the data. So you will notice that the majority of the mini Neptunes with the mass measurements, they're kind of too small for their masses, that they have to form very late. They have to form very, very late. Otherwise, it's just like impossible. But again, to test this in more detail, we do need a larger sample and larger data set for the masses, because we only have 10% of the detected planets with mass measurements. So unfortunately, a lot of the masses for the small planets that are so small that currently it's like impossible to really detect them. But there are future instruments that are being commissioned. We call them extreme precision radial velocity instruments that are being commissioned on top of some of the more powerful ground-based telescopes that are currently on site, and also that are upcoming, called extremely large telescopes. Those are those are sort of like decade-long time scale that we're looking at. But like in astronomy, like for these sciences, like you do have to plan quite far ahead. So that's something to watch out for. Something that we can test a bit more near future is to look at that requirement for the creation of the giants. So I mentioned how they need to be massive cores, but how exactly massive, like to nail down that number, it actually depends on quite a few things, including what kind of chemical composition the planets are accreting, like what kind of material is the planet accreting. So that's what is shown here. So just graphically, these points, like those are all sort of like what is that criteria, that critical core mass that sort of boundary that determines whether a planet will become a gas giant or remain as small mini Neptunes. And you'll see 2 different points over here, 2 different sort of tracks that correspond to the different compositions. So these are like more dusty material, and this is a less dusty material. And this sort of difference is big enough that it should be testable when we take a look at the overall mass distribution of the total mass distribution of the planets. So that is upcoming with the NASA's Roman Space Telescope. This is a microlensing mission, and it is uniquely capable of getting the sort of like overall distribution or histogram of the planetary masses at the intermediate distances. It is uniquely capable of probing that is something akin to like the solar system version 2. And this should go online 2 years from now. At least that's the plan. So, but we'll see. We'll see whether that will happen. So something that I'm really looking forward to, and because we're combining this to sort of like different chemical composition of the material that the planet is accreting, that is something that is being tested right now with JWST, where we're using lots of JWST time to probe the sort of the exoplanet atmospheres to figure out what they're made out of. So there's some I think some exciting synergistic efforts between the 2 big missions with NASA. And then you can also ask further questions at a more fundamental level of sort of like more fundamentally, can we make prediction for sort of like just overall distribution of core masses? And while this is a really fundamental question that I'm also personally invested in, it's a very difficult question because to really get at this, we need to have a really good understanding of the birth conditions of the planets, as in we really have to understand in detail what the dust, what the solids and gas is made out of, and like what the sizes of the grains are. And all of those are extremely difficult. But because I'm at Charlottesville, NRAO, I think I have to mention this, with ALMA. ALMA was another instrument that made the revolutionary headways into this. Because thanks to ALMA, we now have some idea of how, at least how the dust grains organize themselves in these disks. And they organize themselves into mostly concentric rings and sometimes spirals. It's not a smooth disk at all. So I'm pretty excited about this because using this, we can actually get some of like the key parameters that can tell us what kind of planets, what kind of core masses we're going to end up with from the very beginning stages of planet formation. However, ALMA, its resolution is such that we can only probe the outer reaches of planetary systems well beyond the orbit of Jupiter. And most of the exoplanet detection is well inside the orbit of Jupiter because that's where it's easier to detect planets. So again, we do have to look quite far ahead into the future. So there's a NGVLA, next generation VLA, very large array, that's been commissioned and and to probe those inner regions inside, around and inside the orbit of Jupiter, so that we can start to make that one-to-one linkage between the disk observations and the planet and the exoplanetary discoveries. And this is not coming up until like 3 decades from now or so. But that means that there's a lot more room for theorists like me to play a role, because we need those theoretical predictions and expectations, so that we can help with the instrument design, and also to help plan for observations and make a predictive theories that can be tested with all this ongoing and upcoming missions, both at the disk level and also for the exoplanet discoveries and observations. Thank you.
Quick question, does Saturn, the rings of Saturn, or that material between Mars and Jupiter, does any of that help in your modeling, or is that just unique to our solar system?
I think we do expect, especially if we can find more giants at those like large distances, it's actually easier to have like ring-like system or moon systems when planets are farther away, just because like there's the easiest way to say this is that there's more room to fit those in and have them stable. So,
but if
yeah.
you're modeling exoplanets,
Yeah.
We have our own solar system where right now you have a whole bunch of material between Mars and Jupiter.
Mhm,
You know, will that form a planet at some point, a billion years from now, or is that?
I don't think there's enough material there. But those are usually considered as a leftover material from planet formation, and we actually see them, like for example, if you look farther away, like Kuiper belts, there are exo-Kuiper belts that we observe called debris disks. So that can also help us, like even from like exoplanet discovery, because like sometimes they come in really weird shape. A lot of them do. That tells us that there must be some kind of perturbing planet there. That's otherwise extremely difficult to just. Yeah.
So I got a question. I guess as a theoretician, I see model development in 2 different thrusts. One is incorporating new physics, or not new physics theory, but more physics ideas into your model. Is one approach, and the other one is using the existing physics in there, exploration of the parameter space. What's the initial conditions and things like that? Could you kind of contrast maybe where you fall in that, or where the major thrusts are? Is it incorporating of new physical processes, or tuning the existing physics to kind of match the initial conditions? Where do you think you lie there, or
Yeah.
is that not a?
Yeah, no, that's a good observation. So I think I'm closer to the former,
Okay.
where I start from the basic physics principle and then see how that compares against the observations.
So kind of a follow-up to that then is how, and this is something about the astronomical theory, the theoretical community, astronomy, are these models, like you're using a standard model that you've extended and other people use start a similar thing and they extend it in different ways? Or is everybody has their model and they're kind of working it, the whole thing from scratch here and from scratch here? Trying to see what the nature of collaboration is between what the modeling work you're doing and the modeling work maybe your peers are doing.
Yeah, I think theories come in like all different kinds.
Okay.
And yeah, I should be careful. Yeah.
Well, you started it. You started with something.
No, but they come in all different kinds. It also depends on the question that we're interested in, right? Like there are certain questions where it's like a bit of a open field. As it has not matured yet. And if it has not matured yet, then it's actually easier, well, more natural to go from, okay, like, can we start from like basic physical principles and like just build on from there? But if a certain question is already matured and there is already, like, as you say, like standard or established model, and like I noticed how that model is the missing like one key physics that, and that's why it is not explaining a one particular observation, then that's also valid, right? To take that model and like put in that extra physics so that I can explain that question that I would like to answer. So it actually depends a lot on like what is my research interest and like what kind of specific question that I want to answer.
Okay, thanks. I Googled it, smoke particles are 2.5 microns.
Oh, okay, so it's kind of similar.
Maybe, but
Yeah,
so the far end of your scale is
micron.
1 micron?
Yeah.
Yeah, so.
Can you tell us how you think the cotton candy planets form?
Yeah, so I can. So the idea is, to go back to the metallicity, the Z. So if the envelope is not too dusty, either it's like it doesn't have enough dust, or the dust grains have like coagulated and rained out. And if that happens, then it doesn't really act as a heating source. Like it does not act as a blanketing effect of like keeping the planet hot. And at that point, if you go far away enough from the star, then the envelope becomes very transparent. So it becomes very easy to cool off. So it's very easy for the planet to build like very thick envelope, even if you started with a very relatively low mass rocky material.
So it just stays cool the whole time, kind of?
Yeah, it just like keeps on collapsing and cooling, and it can accrete a lot of material.
Thank you.
Yep. Yeah.
I've heard of like other exoplanets where they think that it's like raining diamonds or like kind of some like really like just like surreal. I'm curious like how we're able to like detect things like that or like figure out what material they might be made of or like learn other things that are like just like other characteristics about these planets. Like I don't know how we're detecting those things, but it seems so interesting.
Yeah. So before JWST, it was just like mass and size. And if you only have mass and size, you cannot really tell much other than it's just like one particular density, and like it comes with like so much degeneracy. Like it could be like super thick water world versus like very thin hydrogen helium dominated envelope. But at least with JWST, we can probe at least the upper layers, certain upper layers of the envelope. And sort of similar thing to what I mentioned about like the spectroscopy, like I think this crowd knows spectroscopy. Yeah, spectroscopy. So then like, we can figure out the molecular features, right? And that tells us like at least what the upper layer is made out of. The crux there is that we don't actually know what the interior structure is made out of at that point. So there's a lot of ongoing sort of effort in the community trying to see like how can we say anything about the interior with that limited knowledge of just the upper layer composition.
Have we gotten to a point yet where we found exoplanets that have liquid water close enough to the sun to be kind of Earth-like? Do we know anything about any planets like that yet? Exoplanets or no? Not yet.
Liquid water?
Liquid.
Oceans.
Ocean, so it's not an ice planet. It's
Oh, okay.
similar to Earth, like our atmosphere.
Yeah, so I think we have some steam world candidates. So water, but probably not liquid. Because like if you want to talk about liquid, then you want to probe the surface. And the
Okay.
temperature has to be just right so that like it remains like liquid on the surface. And I don't think we can probe them because like you have to be pretty far away from the star. And again, those are very difficult to probe. Yeah, but like we do have quite a bit of candidates, like what people call water world. What people really mean is that there are some water features in a gaseous form. Yeah.
So there could be such planets in the ones that we've detected, but we don't have the sensing to be able to determine one way or the other whether they are the right mass or temperature to have liquid water on them. Is that the problem? The sensing is the problem.
Yeah, so like we cannot really verify right now. So I mean, like this is where sort of like again like the glint of the ocean like on the surface that would come in handy, but like that's now getting to HWO Habitable Worlds Observatory. That's not gonna come until like many decades from now. Yeah.
I feel like I have to ask this, and I just don't know if you're allowed to share any inside industry secrets about the dimethyl sulfide that was discovered. Is there anything else that followed up since the observation of that in one of the?
No, I keep hearing about it, but I'm only like within my community. Is it not public?
No, it is public, but I don't know if is there anything else that you might be able to share about the.
Other than that, it is real?
Well, right, but they've seen that, but have there been follow-up like studies on it on that planet or looking for other species so far since then that are not yet published or?
No, I think that is the big news that like it is real. Yeah.
Missed the first part of the question. What was the first part
Sulfide,
of the
did you
question?
say?
Sulfide.
You can explain it because you're the planetary scientist, but dimethyl sulfide.
Oh, dimethyl.
It was
DMSO.
exoplanet, and it's kind of a big deal.
Yeah.
It's a good place to go if you want to get rid of your arthritis. One of the uses of DMSO.
Oh, well, it was a mysterious feature in like one of the very early JWST data release. And one of the exoplanet spectra, there was like a one tiny little signature that was kind of mysterious, but then like there was like a whole buzz about, oh, actually, like we can explain it with dimethyl sulfide. So yes, it is. And, yeah, that's real.
Can you talk about how your models incorporate like the development of a magnetic field? And is that modeling, can it only be based on solar system observations of magnetic fields? Or are there any signatures that are observable at a distance, signatures of magnetic fields and intensities and so forth?
Yeah. So for planetary magnetic fields,
Yes.
yeah, that's difficult. But there are some promising avenues. So if there are planetary magnetic fields, it's actually sort of like the weather patterns, or I should really call it just the wind patterns. It causes a drag because like it has to interact with the planetary magnetic fields.
The solar wind, you mean, or the?
No, planetary magnetic
Oh,
fields.
okay.
Yeah, just the planetary magnetic fields. It's gonna drag on the wind. So that drag, you can actually probe. I think you can probe, or at least I've seen like talks. They're talking about how you can probe that drag as a sort of like a shift in the spectra using JWST. So then if you can identify the level of drag, then you can back out the magnetic field strength of the planet itself. Yeah, so that's one promising avenue that I found recently.
And a broader question, just for your entire field of exoplanet study, for you and for your peers, does it all begin with planetary science that's solar system based? Like, is that sort of your foundational study, and then you apply that to the observations of exoplanets?
Yeah, so that's a great question, and that was the case before Kepler. And then Kepler said, "No, sorry, your theory is all wrong." And that's when the theorists and the community started to just go from the exoplanet observation. So it takes a more broader view rather than just focusing on the solar system, which is really just one system out of many.
A lot of us around the world who are engaged in planetary imaging were able to contribute to the Juno program, providing imagery and image-based products during that. And I'm wondering, is there any similar type of latitude for amateur contributions and exoplanet validation in a real way?
So, the only sort of citizen science that I saw was actually with Kepler.
Mhm.
So, and I'm not sure if TESS is doing that as well, but like it has tons of like transit data, right? And it requires, at some level, it requires human vetting at some point.
Yeah.
So there was like very significant like citizen science, and I think it got published too. And it goes into like planet validation for Kepler objects, where we just call out to like everyone in the world, take a look, like does it look like a real planet? Not. So that is sort of the level where I saw for like exoplanet detections.
Well, there's some interesting articles that might be worth looking up. Amateurs with respectable size instruments using mono cameras and photometric equipment have actually done some of this type of work. I just don't know if it's going anywhere when they do.
Right.
I'm curious.
Yeah.
What I've heard is it's ongoing. It's ongoing and the amateurs are sometimes able to verify.
Yeah, I've heard that as well. I'm
Transit
just
detection.
curious as to whether or not there's
You know
a
more about it.
systematic way to do that, like there was with the Juno data.
Right. Yeah, but the transit is the only thing that I know of. I'm not sure about other methods.
Pretty much what we're limited to.
One last question? Anybody? Last question?
I'll go for one. Going forward in the future, you mentioned like habitable worlds, that's a space-based system, I think, right? And JWST obviously is, but then some of these large arrays that are terrestrial, where do you see the major thrusts in answering the next questions? Or is space-based systems going to play the predominant role, or are the terrestrial systems keeping up with that?
I think you need both, right? Like they all play equal parts. So a lot of mass measurements, they will be driven by the ground-based instruments. Atmospheres, you need space-based instruments for that. Yeah, but like you need both, right? And like disk observations, like they will be. I mean, JWST can do some, but especially for protoplanetary disk, they will need pretty large arrays. So like that will have to be on ground.
So the follow-up, that picture that you showed, which is incredibly dramatic, what took that picture? What system?
Sorry, which picture?
I'm sorry, the picture of the actual imaging planets around a star with the starlight blocked out.
Yeah.
What system? Where did that picture come from?
That is a ground-based instrument. Yeah. So like you really need both.
Okay.
Dr. Lee, that was fabulous. When you said you were finished, I thought, wow, 10 minutes, is that all shit? I couldn't be a whole hour. I thought it was amazing.
Oh, thank you.
And, hey, just one bit of information for you. So you were talking about how much cooler it is up in Montreal. Like a week and a half ago, we had a freeze advisory.
Really?
Yeah. Well, here's
I
what.
was wondering, is this normal weather here at this time?
This is fairly weird.
Okay.
Freeze is weird.
I don't think anybody knows what normal is anymore.
Yeah, that's true. Yeah.
There you go.
Yeah.
Yeah.
Well, thank you so much for coming all the way down here. And I know you're going to do this NREOT too as a separate issue, but appreciate you coming all the way down here. And what we'd like to do is present you our coveted Cass coffee container. Try to say that 3 times fast. And so, in appreciation for you coming down, it was
Thank you
very
so much.
kind. So.
Yeah.
So we have a few other things that we need to finish up tonight, and has everybody signed the little star thing? Everybody?
I think I got it around everybody.
Good.
Yeah, better to do it.
So a few things now. Tonight we have the image stabilized binoculars going to, right? And then Nolali, she just left, but she was going to take the what do you call it? Unistellar. Thank you so much. So right now that's hanging out. Who's got the next? Who has the?
She's just moving her car.
Oh, could be. Yeah, I mean, we have it here. It's not even in the building. We have to go grab it. So, who has the Sea Star?